Guys, so first things first, I'm going to construct a problem for you and then we're going to talk about the different ways to solve it. So we have a square, which is a regular polygon with 4 vertices, and we have the center of the square. We have a midpoint between the center and a corner, and we have a midpoint between an opposite side. We have 2 segments, and my claim is that this segment J and this segment K are of equal length and that they are also perpendicular. So let's go ahead and look at it in the GeoGebra perspective, and you can see here that J is equal to K no matter how big or small the line segment AB is, and that J and K are always perpendicular to each other. So we're going to talk about 2 ways to prove that. And the first way is going to be a very traditional, what we would do in just an algebra technique. So to get to algebra, we're going to throw it on a coordinate plane. We're going to go ahead and put point A at -2 on the x-axis and point B on -2 on the y-axis. And what we get is now we have coordinatized points. We have a coordinatized G, F, and C. So we can do some algebra manipulation with it. Alright, so from our algebraic perspective, we have all these facts right here, and we are trying to prove these 2 claims. So the first thing we should do is actually find what F and G are. So we have our midpoint formula right here. So G is the midpoint between A and B. So G equals the -2 plus 0 over 2, and then 0 minus 2 over 2, which is equal to -1 minus 1. And then for F, it is the midpoint of AB. So F is 0 plus 0 over 2, and 0 plus 2 over 2, which ends up being 0, 1. So we're just going to go ahead and write that over here, just to keep all of our facts in the same place. So then we should find the distance of GF and FC. So let's start with GF. So we have our distance formula right here. So distance of GF we have the distance equals this big square root of 0 plus 1 squared plus 1 plus 1 squared. We'll close that square root off. When we simplify this, we get 1 squared plus 2 squared, which equals 1 plus 4, all under that square root, which is equivalent to square root of 5. And we are going to check that against the distance of FC. So here we have the distance And we still have this big square root because of our formula. And we get 2 minus 0 squared plus 0 minus 1 squared. And this is equivalent to 2 squared plus 1 squared, which, as you can see, this is 4 plus 1 under that square root, which is still that root 5. So the distance of GF is indeed equal to the distance of FC. So that proves our first claim. Now our second claim is that GF is perpendicular to FC. So let's do a new sheet of paper for this. So this is a recall that two lines are perpendicular if the slopes of those lines is the opposite reciprocal. So we're going to find the slope of GF. So slope, we usually substitute that lowercase m in for, and this is equivalent to 1 plus 1 over 0 plus 1, which ends up equaling 2. And then we have the slope of FC, which we have 0 minus 1 over 2 minus 0, which is equal to negative 1/2. So reciprocal means that you flip your fraction. So 1/2 is the reciprocal of 2, and then opposite just means you add that minus sign in. So we know that GF is perpendicular to FC. And that proves our second claim. Alright guys, so our next perspective is going to involve complex numbers, which I know is a little scary, but hopefully after this proof you can see that they're just a tool that we use to make our calculations easier. With the complex numbers, this proof will also include vectors, which will be a little bit of a new perspective, and then we're going to use some vector properties that we know to prove our claims that the segments are the same length and they're also perpendicular. So first we're going to find these vectors. So you see this vector u we have right here. We are interested in moving this vector u so that it comes from the origin. So all you have to do is take this vector from E to F and this vector from C to E, and you are going to add them. We add them tip to tail, so we're going to take the tail of this guy and drag it here. We know it's 2 unit lengths, so we will go 2 unit lengths this way, and our resulting vector will be this. So this new vector right here is equivalent to u. And similarly, for the other vector that we need, let's scroll back up here. This j vector, we are interested in the vector from G to F. We are going to, once again, go back up E to F, and we are going to use this vector from G to E. And this one's a little bit more challenging, so we're going to find the length, because we're not quite sure the length, and we're going to center it right there. And then we have to make sure that angle stays the same, so we're going to use the parallel lines here, and they're going to go through there, and we know that that vector is now right there. So let's find that intersection, and thus our resulting vector from E all the way out to J. And as you can see, because we use our parallel lines, this vector is equivalent to this vector. So now we have our two vectors that we will be working with, and we have a new way to prove our claims. Alright guys, so our next way, as we talked about earlier, is going to be with complex numbers. So we have a kind of a new notation. So if we're given this point, AB, this is going to be equivalent now to A plus BI. So we can take all these points and transfer them into the complex plane, but we are actually only interested in a few points. So C is one we are interested in, and this is going to transfer so that A becomes that 2 plus 0I, which is just equivalent to 2. E is another point that we are interested in. This becomes 0 plus 0I, which is actually just 0. Super lucky for us. F is a little different. We get 0 plus 1I, which is just equal to I. Ooh. And then we get G, which is minus 1 minus 1I, which is minus 1 minus I. So we kind of have our new frame of reference that we're thinking in things from. So going back to the video, we discovered these vectors, that this vector CF is equivalent to EF plus CE. However, we don't really have a vector that starts at C and goes to E, so we can think about this as EF minus EC. So now we have this vector that starts at the origin, and all we have to do is plug in 2. So we have that CF is equivalent to, we go to F, which is I, and then we go to C, which is minus 2. Okay, and similarly, we are going to do this for GF. So we have our first section up here, and our second section right here. We learned in the video that GF is equal to EF plus GE. But once again, we want the vector to start at E, so we're just going to go ahead and take the negative to switch the direction of the vector. And then we have a vector that maps to F, which we know is I and then we have this vector G, which is going to be, it's a little bit of a handful, minus 1 minus I. So let's go ahead and simplify this a step further. We can distribute that negative sign, so we get I plus 1, and then we distribute it plus I. So we get the vector GF is equal to 2I plus 1. So this is our next vector. So now we have two vectors, which are the segments that we want. So we have a theorem. I'm going to go ahead and write it out. To show that CF and GF are congruent, which means they're the same size, and perpendicular, we can show one vector is plus or minus I times the other. So basically this is a fancy way of saying if we take g of f and multiply it by I or minus I and we get c of f, then they are indeed the same length and perpendicular. So let's take g of f and we're going to multiply it by I. And we get 2I plus 1 times I. This is going to equal 2I squared plus I. And I, so let's go back up here, I equals the root of negative 1. So I squared equals the root of negative 1 squared, which is just equal to minus 1. So we're going to use that fact right here. So we get, this is equivalent to minus 1 times 2 plus I. So we get g of f times I equals minus 2 plus I, which also equals I minus 2. And as you see, that is equal to c of f. And that's it. So I totally get that complex numbers seem really scary. You get this I, you get this thing, which you've been told forever is not in okay form, but it makes a 2 to 3 page long proof a very simple process.